Hey everyone, my name is Anil.
Hi, my name is Maxwell Bland.
Stuart Grant, reporting from Vancouver, British Columbia.
Today we're going to talk about SmartNIC isolation with FairNIC. SmartNICs are programmable network interface cards that enable hardware acceleration for networking applications. Recent work has shown that a variety of applications from key value stores to data analytics can benefit from SmartNIC acceleration. Cloud providers like Microsoft Azure have deployed SmartNICs in their data centers to accelerate their networking infrastructure. However, cloud tenants are yet unable to enjoy the same benefits. Let me show you why with an example. Imagine a tenant running a key value store application in the cloud. In cloud setting, tenant applications are run in virtual machines on a hypervisor to prevent them from affecting other tenants. Past work has shown that the key value store can benefit from SmartNIC acceleration. To avail these benefits, the tenant would need to download the code onto the SmartNIC. However, downloading code onto the NIC is currently not allowed in the cloud as the code is untrusted and could affect other tenants using the NIC. To enable this scenario, clouds require a hypervisor-like solution on the NIC itself. In this work, we propose a system called FairNIC that enables multiple tenant applications to safely download their code onto the SmartNICs. Complete isolation requires both performance isolation, which enables quality of service guarantees, and security isolation that addresses issues like memory safety, side channels, etc. In this work, we focus exclusively on performance isolation. We assume an environment where the tenant applications are generally trusted from a security standpoint. An example of this environment could be a software as a service deployment model where the cloud providers write and compile the set of applications that are downloaded by the tenants onto the SmartNIC. Performance isolation is still necessary in this setup. To motivate this, we run an experiment with a key value store that is accelerated on the SmartNIC using on-NIC caching. In the plot, you see the distribution of latencies of the requests served by the key value store when it is running alone on the NIC. Next, we run another SmartNIC application alongside the key value store application that contends for the same SmartNIC resources. In absence of isolation, there could be resource contention, and this could affect the key value store performance, whose latencies could go up by 2 orders of magnitude. With isolation provided by FairNIC, which we will discuss shortly, the performance goes back to normal.
What is this? In order to understand something about the problem of performance isolation in a multi-tenant SmartNIC environment, it is critical that we understand something about the architecture and the functionality of SmartNICs themselves. For our experiments, we used 2 Cavium liquid I/O boards provided generously to us by Marvell Technologies. The boards are SoC based, meaning they support offloaded C applications and are also capable of handling a 25 gigabit per second line rate. We subdivided the architecture of the boards into 4 key categories, the first of which is packet I/O. The ingress and egress engines are configurable and capable of handling a 25 gigabit per second demand. However, by default, neither of the engines supports FairNIC or multi-tenancy. In FairNIC, we modify these engines so that multi-tenancy in the SmartNIC environment is a real possibility. We also considered another 2 architectural categories relating to programmability. Programmability, in many ways, is what the SoC SmartNICs are known for. Recall the capability of being able to offload applications. The processors and memory, and more specifically, the cache, were all modified by FairNIC in order to support multi-tenancy. The 4th architectural category that we consider is that of coprocessors. The coprocessors allow the SoC SmartNIC to perform a rich set of tasks, such as encryption and compression, while keeping up with that high network speed.
In our paper and 20-minute talk, we discuss resource contention on SoC SmartNICs at packet I/O, on cores, in caches, and on coprocessors. For this 10-minute talk, we concentrate only on coprocessors, as they are a somewhat unique aspect of SoC SmartNICs and one which required an interesting solution for isolation. The coprocessor is a piece of hardware which performs functionality in an accelerated way. Specifically, these are common functionalities such as generating random numbers or zipping files. The latency at which the coprocessor is accessed is a direct fallout of the functionality which it performs. So when generating random numbers, this is a constant time function, and when zipping files, it's proportional to the size of the input. Coprocessors have some bandwidth at which they can perform their computation, and this is very similar to egress or ingress bandwidth. So one app which is making constant requests of very large files to a zip offload could cause another application to be starved, or not necessarily starved, but receive performance below what it is asked for. And this is because access to the coprocessors is guarded via a FIFO queue. Ideally, we would have a deficit round-robin queue guarding access so that we could have isolation and performance guarantees, proportional to the request rate. We developed one of these in software, but found that the overhead of intercore communication exceeded an acceptable bound. And in some cases, this meant that the accelerator itself performed lower than performing the computation on an isolated core. In order to have a solution for this problem, we took a page out of the distributed systems literature and used a distributed token rate limiting algorithm in which each application in isolation generates tokens which guard its requests to the offload. The aggregate number of tokens which are generated per second is proportional to the rate at which the zip offload, or any offload, can perform its requests. And what this allows is for applications to essentially guard themselves with zero need for communication. Now, is this a practical solution for accessing coprocessors? We develop a test in order to demonstrate the efficacy of our approach. We developed two applications, two versions of OVS, the first of which zips packets as they arrive. On this plot, we have as the x-axis the packet size, and on the y-axis the megabits per second of throughput at which the coprocessor is processing. This is proportional to the rate at which it achieves is proportional to the packet size. To introduce contention, we added a second OVS, which for every packet zips it 100 times. Note that due to the first in, first out queuing in this non-isolated case, the performance of OVS 1 drops down to nearly that of OVS 2. When we enable the distributed weighted token rate limiting, OVS 2 is not able to make as many requests, and because of this, its rate drops, whereas OVS 1 returns to nearly the same performance that it achieved when running with all of the resources of the NIC at its disposal. This demonstrates that our approach does not introduce substantial overhead, and that it is a practical solution to coprocessor isolation. Thank you for watching our 10-minute video. We hope that you take the time to watch our 20-minute one and to read our paper. To summarize, we provide FairNIC, which is a framework for performance isolation on SoC SmartNICs. We create a number of lightweight isolation techniques which we employ on these SmartNICs, and we demonstrate them in a realistic cloud setting. This work has been done out of the University of California, San Diego, and UISUC. Thank you for
Thank you. This is great. Question is, to what extent do you think your solution is coupled to the specific architecture of NIC you've been using?
Yeah, thanks for the question. That's a really great one. The same one that we got from multiple reviewers as well. Yeah, so there are a variety of SmartNICs out there. Specifically, there's FPGA ones, and within the SoC SmartNIC ecosystem as well, there are multiple different architectures of these SmartNICs. So we, with FPGAs, when we compare it to them, they are fundamentally very different, and we don't really think that these solutions would generalize very well to them. But as far as SoC ecosystem is concerned, the architectural components of different SoC NICs are still similar, although the way that they are arranged on the NIC might differ. So, and in this paper, we propose a per resource sort of isolation mechanisms where we propose independent solutions for each resource. And that makes it like more flexible. And, you could turn off, on and off any sort of these isolation mechanisms at any resource the way you want. So short answer, yes, to some extent, it is generalizable to other kinds of SFC SmartNICs. And there is a section in the paper on this if you want to take up.
All right, great. You answered a second question as well. That's great. Next, can FairNIC isolate traffic when the DMA engine becomes congested?
So I'm guessing the question is also related to whether we isolate. So in our NICs especially, we did not find some resources like PCIe bandwidth or some other internal buses, or in this specific case, the DMA engine, to be the bottlenecks. Like they're not really become bottlenecks at the line rate at which our NICs are processing. So we did not really take a look at them. But yes, it might become an issue if we go to higher packet rates or NICs that process like at 40 gigs or 100 gigs.
All right, so how do you handle contention due to ingress traffic? Do you need to drop packets in the NIC RX queues?
That's a really good question. So they obviously, like, there's an ingress only like to a certain extent it is in the control of the NIC itself. Obviously, data centers, they deploy some sort of sender side admission control techniques to isolate the ingress traffic coming from different parts of the data center. But we considered that out of scope for this paper. But one thing that we did regarding ingress was we have an ingress engine on the NIC that packets hit the first they arrive on the NIC. And by default, the engine itself does not differentiate between tenants between different traffic and puts them in the same buffer. So that creates a head of the line blocking sort of situation for multiple tenants. So what we do there is separate these buffers for different tenants. So that there's no head of the line blocking, and then each tenant has its own sort of pipeline till the packets get to the other resources later in the stages.
I see. Thank you. And last question, I think, what are the challenges of porting FairNIC's ideas to inside the switch for in-network compute?
That's a question that we were sort of expecting, and I don't think the mechanisms themselves are very generalizable, because fundamentally these architectures are very different. But there might be lessons that are that may be sort of that might apply in case of switches as well, which is that these devices are very resource constrained. They have these very high performance requirements. They have to run at line rate, and so you have to necessarily make this trade-off between how lightweight your isolation mechanism needs to be, and what kind of properties you want to attribute to it, like work conservation and all that. So in our paper, we went for static partitioning of a lot of resources just because we want them to be very lightweight. And so we gave up on like some very desirable properties like work conservation. So that might be, there might be similar trade-offs that you might need to make when dealing with switches as well.
Okay, great. Not only you enabled fair sharing on SmartNIC, but you also enabled fair sharing of screen time during the video.
That was very intentional.
All right, so here's a question from Zoom. To what extent do you think your solution is coupled to a specific architecture of NIC that you have used? And what are the takeaways that you can generalize across SmartNICs?
Right, so the question of generality is sort of a subtle one, and I'll have to describe the different architectures of SmartNICs very quickly. The first of which is that there's two kinds of SoC SmartNICs that are largely produced, one of which is on-path SmartNICs, which we have, in which every packet is routed through a core, and then there's off-path SmartNICs. The kind of other example of this that's very common is FPGA SmartNICs. Now, in the case of both versions of SoC, I would say that our techniques generalize completely. In the case of FPGAs, it's a little less clear. And so we take a very software-based approach, which would not actually work on an FPGA. However, some of our static partitioning techniques would hold up absolutely. There's a project called NICA, which I believe is ATC19, which has a similar approach like this. But we take a very resource-based approach to resource isolation. So for example, our cache partitioning algorithm is completely general, and it would work on an N host as well as it works on a SmartNIC. Really what we've done is taken a very close concentration on the need for high bandwidth. So our solutions are very lightweight, and that's really what makes them special and specific to SmartNICs. So they're fully general, but they might not be perfect for other places where you might want different performance guarantees. Yeah.
All right. So one other question on Zoom is that what are the challenges of porting FairNIC's idea inside the switch for a network compute?
Interesting. So I guess the question is, I'll try to restate it, which is that do our techniques apply to programmable switches? And I think the answer to that is no. I'm not an expert in the architectures of programmable switches, but I'll again give an answer that's very similar to what I said about FPGAs, which is that even though the architectures are different, some of the lessons that we've learned along the way might still be useful. And so one of the things that we found was that in a few cases, doing things like static partitioning, for instance, were by far the best solution because they avoided things like L1 cache pollution, and doing things like statically partitioning cores, for instance, also avoided L1 cache and also the overhead of context switching. Now, not that you would be doing context switching on a programmable switch, but there might be other resources which just the idea of switching them between different applications could induce overhead, which would cause their line rate to just dramatically drop. And we found that in a lot of cases, so I think that our solutions would generalize there. But as I said, I'm only have a superficial knowledge of programmable switches, and I think their pipeline architectures have very special components to them, which would need their own solutions.
All right, interesting. One final thought is, if you watch the video from the Slow-Mo authors, are you familiar with the work?
No,
about
not unfortunately, but I can try to weigh in.
Yeah, that's also about placing NFVs, different NFVs on the same host, and can we predict the performance, right? So it's more, it's also related in the resource isolation angle. So I wonder if you can learn. I was wondering if you could learn anything from the work of Slow-Mo. Yeah, so that's something that you can take a look after.
I'll definitely put an answer on the Slack channel, but I would need to understand the context in which that work has been done for me to really give a good answer.